All right, welcome back. Get your seats. All right, so we'll start a different lesson. So for the next few lessons, we're going to talk about different important combustion regimes and what chemistry matters. And then for each of those chemistries, we'll talk about if you wanted to be able to compute them and measure them, what are considerations that you need to consider. We'll talk a little bit about the macrochemistry, and then we'll talk a lot about micro stuff that you have to do if you're trying to compute or measure those particular quantities that matter for that chemistry. And then we'll come back to a different combustion regime that has some other chemistry and talk about the things that matter for that one. So the first one we're going to talk about is the exhaust region after the combustion is finished. And in that region, the temperature is very high because you just burn the stuff. And the reactions are really fast, partly because the temperature is really high, so all the rate coefficients are fast, and also partly because typically after combustion you have a very high concentration of radicals like OH, and those things catalyze the chemistry, make it really fast. And so typically you're very close to equilibrium for most of the reactions. And so it's not a bad approximation to just figure out what's the equilibrium state, and then computing the equilibrium state in the exhaust region gives you pretty accurate estimates of the concentrations of all the species there. All right, so what we learned in the first lesson was that the fuels are both really good and really bad. Right? They're really good if you want to take your car to drive to New York, or if you want to get in your airplane and fly to Los Angeles, or to Saudi Arabia, wherever some of you guys came from. It's really nice to be able to have fuels. It enables that. It's also actually relatively cheap, at least to produce, and it's very convenient. However, the current system has a major weakness related to the greenhouse gas emissions. That's pretty fundamental and hard to overcome because there are very few elements that have the energy density that we would like, and one of them is carbon. And that's the one that is the biggest culprit for the greenhouse gas emissions. And so to beat that problem, there's kind of two approaches. One is to try to improve the efficiency of the system so you can get the same standard of living and quality of life, but emitting less CO2. And another direction is to try to just switch to a different energy carrier that doesn't have the greenhouse gas problem. But if you do that, for sure, you'll pick up other problems. So that's what we talked about. My research is largely based on the idea of, well, if we're going to switch to an alternative fuel, we really need to assess which alternative fuel could actually work. One of the possible solutions we didn't talk about too much is to switch to biofuels, fuels that you can make from biomass, or fuels that you would make by recycling CO2. If you capture CO2 and then make it back into a transportation fuel, that would be another possible solution. But then you need to, if you're going to synthetically make the fuel, you have a lot of choices about what to make. But if you're going to assess what you want to make, then you really would like to say, well, how can we figure out which fuel is really the best? And that would require understanding the chemistry. Or it might be able to make the thing that's easiest to make, and then you have to assess is it actually going to work for you. So you need to have know the chemistry for it. Another whole topic is the fuel chemistry. So once you decide to get into predicting the behavior of even an existing fuel or a new fuel, then you have to worry about the fact that you need to predict a lot of reactions, a lot of species, a lot of rate coefficients, and as we'll see in a minute, a lot of thermochemistry. And in general, combustion chemistry is tricky and complicated. It's not a single step. Even the simplest fuels have dozens of reactions. And for the realistic fuels, you're easily getting into thousands of reactions. And immediately that's super complicated. It's hard for humans to keep track of in your head. It's hard to estimate all those parameters. It even can be hard for the computer to integrate the equations. But it matters. The different fuels actually do behave differently. And it's because of these chemistry details about exactly how they react is why they behave differently. And so if you want to understand that, if you want your model to be faithful to that, you have to capture those differences. So you get into a lot of details. All right, so our plan of attack is, let's start with Thermo. Thermo is simpler than kinetics. And so we'll talk about how we get Thermo. And a lot of Thermo is related to statistical mechanics, equilibrium statistical mechanics, so we'll talk about how you do that. And then a little bit later, we'll do simple rate theory. We showed already the concept of how you do rates, either for cars or for molecules, by drawing dividing surfaces, boundary surfaces, and then counting fluxes across the surfaces. And we even showed how you get a relatively simple formula from classical mechanics for the rates. So we have an idea about how to do it, and we'll talk more about how you do the computations. It turns out that the rate theory gets quite complex pretty fast, and so we'll talk a little bit more about that. But if you really want to get into really fancy rate theory and try to get very high accuracy calculations, you're highly recommended. You should take Dr. Combustion's class in the afternoon. And then we'll talk finally about, after we know how to do Thermo and we know how to do rates, how do we assemble whole mechanisms? And my group specializes in that problem, and I'll talk a little bit about how we do that. All right. So combustion chemistry really varies a lot with different reaction conditions. It covers a tremendous range of temperatures and compositions. And when you change the temperature and composition a lot, you really change what happens. And you've seen this yourself. So how many of you have used a gas stove? Have you used a gas stove? Right? So you turn the gas on, and when you first turn it on, there's no fire. And then there'll be some kind of a igniting mechanism, or you use a match, and then you have a fire, right? And so that same mixture, that fuel-air mixture, changed from being completely unreactive. It's just a cold flow of methane, basically, in air. And suddenly turns into this completely different thing that's a fire. And you look at it, part of the fire is glowing blue, some part might be glowing yellow. The temperature field is different in different locations. It's like really inhomogeneous. If you change the position of your pot relative to the fire, you get quite different heat fluxes. So it's really a very highly inhomogeneous situation. And all you did was add a spark, right? So and that tiny little spark suddenly changed it from one condition to a completely different condition. And if you try to turn back the flame, the methane, you'll start to make it flicker and become unstable. And then if you measured, you'd have a lot of emissions. You get a lot of aldehydes, for example, formed from a natural gas flame, and if you run it poorly like that. If you blasted the methane in too fast, you actually wouldn't be able to get good fuel-air mixing, and you'd have rich regions, and you would actually make particulates. And if you'd see you'd make soot. Eventually, if you go down to in your basement, if you have a hot water heater, if it's burning for a lot of years, if you look around the burner, it's all covered with soot, even though it was burning natural gas, because the burner's not perfect, and there's some spots that are rich, and you make a little bit of soot, and it gradually builds up over time, and eventually you have to hire somebody to come and clean your burner off or replace the burner to make it still work. So the chemistry is wildly different. Sometimes you get aldehyde, sometimes you get soot, sometimes you just get CO2 and water, every different thing. These things really matter. So aldehydes are toxic. The soot particulates are a major cause of mortality. So these things, it really matters that you make it burn cleanly is a lot better than burning poorly. This is a picture of how inhomogeneous the systems are. So this is a flame front, and this shows the temperature in degrees Kelvin over here. And you can see that right here is the flame. So you come in cold flow of, say, fuel and air, and out here is the hot flow above 2,000 Kelvin. And in just a period of a couple millimeters, you have a change of 1,500 Kelvin. So that's a pretty dramatically inhomogeneous system. If you look at the concentrations of species, you have your fuel and air coming in, and basically all the fuel is gone in a few millimeters, or less than a millimeter. Yeah, here you go. This is 1 millimeter, right? So this is half a millimeter. So this is half a millimeter. You've gone from lots and lots of methane to none, and you've gone from zero steam to a lot, and CO comes up and goes down, and all these things happen in this region that's less than 1 millimeter thick. So really dramatic changes. And in Professor Matalan's class in the afternoon, he'll be talking a lot about how the approximation that was often made for a long time is just to assume that this is infinitesimally thin, that somehow this fuel and air instantly turns into CO2 and water. And it's not so bad for a lot of purposes. This is such a thin flame area that if you assume it like a delta function, it's not so horrible. And you can see you get changes in the concentrations of all these species. This is a log plot. A lot of species are changing by 2 orders of magnitude over this millimeter. So we're going to try to consider the different regions separately, and we're going to start by worrying about the exhaust region over here. So things aren't changing that fast, and this is kind of close to equilibrium. Relatively simple. Let's start simple. All right, so these are some different regions that we're going to worry about. So first is this exhaust region. Another one is the diffusion flames. I just showed you one of those. No, actually, no, diffusion flames. I showed you a premix flame here. Premix flame, we often worry about flame speed, and the H plus O2 reaction turns out to be by far the most important thing. In diffusion flames, the fuel decomposes before it reacts, and so you have to worry about pyrolysis chemistry of the fuel. And that's usually the main important thing. Some other situations you worry about ignition delay, and there the chemistry depends strongly on the temperature and changes. If you change the temperature, actually the chemistry completely changes. It's not just that the rates change, but the actual reactions change and the intermediates change. And this also depends a lot on pressure and partial pressure of the oxygen and fuel. Then we'll talk about NOx formation pathways. Those are completely different reactions that make the NOx than the main chemistry. And then finally, the partially premixed flames, where you typically have a rich premixed flame and then fuel pyrolysis, and then eventually a diffusion flame. Quite a complicated situation, but this is very important. This is the situation in diesel engines and also in a lot of other burners, like jet engines, like boilers, that we often have the fuel and the air not well mixed to begin with, but in the fuel injection, some of the air gets mixed, so you end up with a partially premixed combustion situation. All these have different chemistry happening. All right, so let's talk about the exhaust region. Thermo is the key, so let's talk about how you do thermo. So all of kinetics is always leading towards chemical equilibrium. And so we worry a lot about the rate of how fast it gets to equilibrium, but it's often better to start by worrying about where you're going. So where is the equilibrium? Where are you going to get to? And you know you're going to get there in some amount of milliseconds, you'll get there. And what's the, if you don't care exactly how many milliseconds it takes you, you just really want to care about what's the equilibrium state. Part of thermo is about phase behavior, things like volatility and miscibility. I'm not going to talk about that, at least not today. We're going to talk instead about thermochemistry, which is about reactions, about bonds breaking and making. And the magnitudes in thermochemistry, the scale is scales of like 50 kcals per mole, very big scale. In this other part about phase behavior, it's like 1 kcal per mole is the things you worry about for like solubilities and stuff. So it's a completely different scale. And so let's talk about the big numbers first. The big numbers are thermochemistry. And of course, that's where the energy is coming from. That's why a fuel is good, because it carries a lot of energy, because the changes in the chemical bonds are worth lots and lots of kcals. So you get a lot of heat for a little bit of change. So we'll do first law, and then that gives you things like the energy density and the final temperature of a flame. And then the second law is related to a thing called detailed balance and reverse rate coefficients and equilibria. And we're worried about the equilibria here for the exhaust. All right. So there's a quantity that you always look up whenever you start with a new fuel. That's called the lower heating value, the LHV. And it's a thing that you can compute very easily just from the enthalpies. You look up in a table, and what way it's defined is how many carbon atoms times the heat of formation of CO2, how many hydrogen atoms in the fuel times the heat of formation of water in the gas phase. So you take the value for steam, and then you subtract the heat of formation of the fuel, and this quantity is called the lower heating value. And it's lower because we use the gas phase value for steam, not the standard value, which would be liquid water. Okay, and that's because most of the combustion devices don't make liquid water. They release the exhaust as a gas, as steam. So that's really how much energy you can get out. You really can't get that last bit out very easily. And so this number you compute this way would be lower than you would measure in a bomb calorimetry experiment. So bomb calorimetry, what they do is you make a metal can, You put your fuel and some oxygen in it, you close it up, you stick the whole thing inside. Typically, you submerge it in a little bit of a bottle of water and some water, and you have a thermometer in the water, and you light it. You have a spark, and the fuel burns up, and the can gets really hot, but it's sitting in the water, so the water temperature rises. And at the end, after you wait for a while, the whole thing gets back to stable equilibrium, and you measure the total delta T. And if you know the heat capacity of the water and the can and your starting material, and you know the delta T, you can work out how much heat was released overall. So that's a very standard old-fashioned experiment, and that gives you the numbers that are called the higher heating values, because in that experiment, all the water vapor basically condenses and ends up as liquid water. So, that's you get one number. This number is lower than that, so it's called the lower heating value. But this one's more realistic because in a real engine, your water is not coming out as liquid water, but coming out as steam, and so you can't really get that extra latent heat is stuck in the steam, and you can't have access to it. All right, so quiz question for you. Is the LHV a lower bound or an upper bound or neither on the amount of heat that would actually be released when the fuel is burned in an engine where the exhaust is all gas phase? So talk to your partners and figure out. All right, so this time we're going to take a vote. So how many people think the LHV is a lower bound on the amount of heat energy you can get out in an engine, out of the fuel? How many people think it's a lower bound? It's called lower. No? Okay. How many people think it's an upper bound on the amount you can get out? Okay. How many think it's neither? Okay. So the neither is the minority. Let's have a minority report. How about you? Yeah.
For the ice engine combustion, the first is there should have some heat transferred to the water coat, and there are should also some friction. They will waste some energy, and also for some typical combustion mode, for example, dual fuel engine, natural gas dual fuel engine, especially in low load, a lot of natural gas cannot be burned, so it will exhaust to the exhaust.
So I say your arguments are arguing that it's really a upper bound. You could, the better you make your engine, the closer you would get to the LHV. Is that true? The English, yeah, this is the English question. How about anybody else from the neither point of view? Yeah.
I hate to answer questions. Anyways, I thought was that maybe it could burn including something like carbon monoxide. I mean, we're assuming that it's all going to go to water and.
Yeah, that's right. So for sure, you could make carbon monoxide. In fact, you do, right? When you run a car, you make some carbon monoxide. But that would also tend to make this number an upper bound, right? Because you get less heat energy out than we calculate.
Yeah, but you could potentially also go above it. So.
How could you go above it?
Well, I mean, if you were to completely burn it to carbon dioxide and water, and some of the water would do anything.
And some of the water would do what?
Never.
I would liquefy. No. Okay. All right, so I'm going to go with the majority on this one. I think this is the lower heating value is actually an upper bound on how much heat you can get out. And we'll see in a minute that there's several reasons, including the fact that you'll make CO, actually, which is quite important, are reasons why you don't get the full value out of the. And in fact, when you do the bomb calorimetry experiment, you have to do it very carefully to try to ensure that you actually run the reaction all the way to completion. It's very difficult to actually make it go all the way. All right, so this is how we compute equilibria. The reaction is running from reactants to products, but in fact, you never run all the way. So you're releasing some heat, say, as you go, but you're also making some gas, and there's some entry effect, and you get some balance, and there's overall some value of G. And the value of G that's sort of minimized with the correct constraints, which I'll talk about in a second, that's actually the equilibrium state that you should achieve if the reactions all run all the way. And there's a program that does this. In ChemKin, it's called Equil. I think there's a similar program in Kantara. I don't know the name, though. Does anybody know the name of the program in Kantara? Say it louder. Equilibrate. OK, so Equil or Equilibrate, they basically do the same thing, is they calculate the equilibrium composition for a reacting mixture with some constraints. And we need to talk about what the constraints are in a second. So how do they work? So they take as input the initial composition and the temperature. And they also take as input a database of the molecules that you think would exist in the system at equilibrium with thermochemical data about all of them, usually in the form of NASA polynomials. So that's what the programs expect you to provide. And then they typically assume ideal gas, ideal mixture, and adiabatic. Though you might be able to set it to be isothermal as well, I'm not sure. But most commonly you would assume adiabatic. And so then the total free energy of the system with these approximations is the free energies of each individual species times the number of moles. So this is like kcals per mole, and this is number of moles. And you add them all up, and that's how many kcals of free energy you got. But these things, these Gs are not the standard state Gs. They're the standard state Gs plus this factor, which is the fact that your partial pressure of that species is not 1 atmosphere, right? It deviates from 1 atmosphere. So this is the factor. It's the mole fraction times the total pressure divided by 1 atmosphere, the P naught. And here's the mole fraction expression. It's just the number of moles of species I divided by the total number of moles. Then it also constrains that the total enthalpy is conserved, because if you're adiabatic, the enthalpy is conserved. There's nowhere for the heat to go. Adiabatic, so you're assuming like perfectly insulated. And then you also have to conserve the number of atoms. So you have a bunch of equations like this that are the moles of species I times, say, the number of carbon atoms in species I has to equal the number of carbon atoms that was in the system to begin with. And similarly for all the atoms, number of H atoms, number of O atoms, number of N atoms, so on. So you're doing a constraint minimization. You're minimizing this quantity subject to all these constraints equations. And that's the way the programs work. And so it just varies the n's and the t to minimize this total nt subject to these constraints. And I assume most of you have already taken a numerical methods class, and you'll know how you can do these nonlinear minimizations. It's not so hard to do. Note, the program only knows about the existence of the molecules in the database. So it's very important what database you put in here. So for example, if you did not put benzene into your database, then the computer will calculate that there is no benzene at equilibrium, because it doesn't even know benzene exists. But you might have a situation physically where actually benzene might be the major product, right? If you ran a fuel-rich combustion, for example, benzene might be a very important product. If you don't tell the computer that that can exist, it won't allow it, and therefore you'll get a false result where it's going to put those carbon and H atoms into some other species rather than benzene, even though it should put them in benzene. All right? So this is the main flaw of these programs is this fact that you have to put in all the molecules. And any molecules you leave out, it's basically constraining them to have 0 moles, even though they might, in the true equilibrium, they might actually have a significant number of moles. So that's the thing to watch out for here, where you can really confuse yourself, is by leaving out species that are important. All right, so thermodynamic data. why do we need the data? We need to be able to compute these equilibrium compositions. So for example, you want to run Equil, you have to provide that database of thermodynamic data, which is the data for each species. You need them to compute the heat release in the process, like the lower heating value. We already showed that one. We also need them to compute the equilibrium constant for every individual reaction. So we have pairs of reactions, forward and reverse. And as we said, all the reactions are reversible in reality. And the ratio of those two reactions is an equilibrium constant. And the equilibrium constants are related to the thermochemistry. Now, it typically is that you have more reactions than you have species. So each reaction has an equilibrium constant. You have more equilibrium constants than the number of species. However, you can calculate the equilibrium constants from the thermo of the species. So it's like an over-constrained system. There's actually, knowing the thermochemistry of all the species is sufficient to compute all the equilibrium constants. So it's a smaller number of data is enough to compute a larger number. And if you don't pay attention to that and you treat them as just free parameters, the equilibrium constants, it's very likely that your thermo and your equilibrium constants will be inconsistent with each other, or internally inconsistent among their equilibrium constants. And this was actually a famous problem a long time ago in the Livermore database. Livermore makes a lot of models, very nice models for fuels. But originally their solver didn't know about this thermodynamic constraint. So the users had to put forward and reverse rates in that were consistent. But if somebody made a mistake and made an inconsistent forward and reverse, then the whole mechanism would be internally inconsistent thermodynamically and would go to crazy equilibria. It didn't match the thermodynamic equilibria, which is pretty bad. So its exhaust chemistry would be completely screwed up. All right, so watch out for that. You basically want to have the thermo, and then have the computer compute the reverse rates from the thermo and the forward rates. This also means you only need half as many rate coefficients. You don't need to supply the reverse rate coefficients. So that's cutting your work in half. So that's really nice. All right, so we're going to talk right now about some classic thermo and StatMech, and then where we get thermo from, how we measure them, and then the active thermochemical tables, which is the modern way to try to get really good thermochemistry numbers, and a little bit about representation of thermodynamic data. So here's some classical thermo that you guys probably all know, but I'll just remind you about that the enthalpy is the energy plus P delta V, or actually H is equal to U plus PV. Here's the Hess's law, which is that the heat of reaction, which is equal to the weighted stoichiometric coefficient weighted enthalpies of the products minus the reactants. The enthalpy of reaction at one temperature is the enthalpy of reaction at another temperature plus the integral of the change in the heat capacities. Same for the heat of formations, the same kind of formula. The free energy is the enthalpy minus T delta S. The equilibrium constant at any temperature is given by the standard free energy at that temperature. And then these things are the ratios of the product concentrations, partial pressures, with the right standard states. So these A's are the ratios, say the partial pressure to the standard pressure, or the concentration to the standard state concentration. And the standard states of the C and the P have to match the standard states used by the delta G to make these formulas true. So in gas phase, almost always everybody uses 1 atmosphere pressure as the standard state. So there's usually no confusion. But in liquid phase, there's at least 3 different conventions for what the standard state should be. They're all inconsistent. And so if you ever get into something with liquid phase data, you really need to worry a lot about standard states and read carefully exactly what the person meant. And unfortunately, sometimes people don't document it very well, so they'll give you a table, but they won't, in the table won't tell you what the standard state that was assumed, and so you can be really confused. You do need a consistent zero of energy if we're going to use the thermo of the different species in order to compute the equilibrium constants, in order to compute the reverse rate coefficients for us. And what you have typically experimentally is you measure like a heat of reaction of how much the enthalpy changed in the reaction. everything's always relative. So I have, suppose my product is something, I'm trying to get the enthalpy number for that product. I can measure the heat of reaction, and if I know the enthalpies of all the other species in the reaction, then I can rearrange this equation and solve for the heat of my product, the heat of formation of my species that I care about. But it's all differences. Everything's all differences. And really, to make everything consistent, we need everybody to agree on what the zero of energy is going to be. And the community decided that elements in their standard state are the things with zero heat of formation. That's just the definition that everybody agreed to. Now, for theoretical calculations, this is actually not very convenient because some of the standard states are really hard to calculate. So for example, graphite is the standard state for carbon atoms, but graphite is like impossible to calculate with any accuracy. And so instead, the quantum chemists most commonly use a thing called the atomization energy, which is computing relative to the energies of isolated atoms. This is also not that great because it's actually pretty hard to calculate the energy of isolated atoms also because they have really weird electronic structures. So that's a headache of this, but at least you can do it. Another thing that was done originally, the physicists did, is they said, well, let's take all the nuclei and all the electrons and scatter them all to infinity. And we'll call that the zero of energy. Now, that's a really great zero of energy because it's completely consistent. Everybody knows what you're talking about, but it's completely impractical because that number is gigantic. It takes a tremendous amount of energy to rip all the electrons off all of the atoms and send all the atoms and electrons out to infinity. And so you get a gigantic, huge negative number. So if you see a gigantic, huge negative number at the end of your quantum chemistry job, that's what that's supposed to be. But if you compare that to the experimental value to rip all the atoms apart and to ionize them all, it's way off, always way off. And that's because the quantum methods are not accurate enough to predict such a gigantic number. They have a certain number of significant figures, and you've wasted all your significant figures computing this gigantic number. So if even you're good to a tenth of a percent, that's still 1,000 kcals or something. So it's like just not meaningful. So that's not so good. The atomization energies are better because these numbers are smaller, because at least you're letting the electrons stay on the atoms. And so you're still better. But even this is not that great as a way. But that's what a lot of people do. All right. So you're going to mostly get your thermo numbers from tables that some other hardworking thermochemist, probably some graduate student before, spent a lot of time to get the numbers for you, and they put them in the table. And they'll typically have these standard heats of formation, which is the energy that it takes to make 1 mole of your substance out of the elements in their standard states. Usually it's all at 298 Kelvin. And here's, for example, if you take some graphite and some hydrogen and you make it into methane gas, this is thought to be the heat of formation of methane, 74.8 kilojoules per mole. And these guys will be exactly 0 at that standard condition. So that's the idea, is to try to get those numbers. And then if you know the number at one temperature, you can use the heat capacity to get the number at a different temperature. So for example, if I know the enthalpy at one temperature, I can integrate the heat capacity to get the number at a different temperature. And similarly for entropy, you integrate the heat capacity divided by the temperature. This thing translates entropies at one temperature to entropies at a different temperature. So then the challenge really is to know what the heat capacities are, so you know how to do these integrations. And we'll talk a little bit later about how to do that, where they come from. Once you have the enthalpy and the entropy, you can construct the free energy, and then from the free energy, the equilibrium coefficients, which are what we're going to need to get the relationship between the forward and reverse rates in our models. And also to get our ultimate equilibrium, right? It's from the G. Note that none of these quantities depend on the pressure, because these are all for standard state. So you've already pre-specified the pressure, really. It's all for 1 atmosphere. The same K equilibrium is the same at all pressures. And to make this work out, if you have a non-ideal gas, what they actually do is they hide the non-idealities inside these coefficients called activity coefficients or fugacities. And if you ever get into that case, I highly recommend you go to a thermodynamics textbook and read about how to do it correctly, since it's not so simple. But in combustion, most of the time, we're in the ideal gas approximation is accurate, so we don't have to worry about it too much. the heat capacities are a function of temperature, and they're expressed in several different formats, which causes a lot of headaches and potential screw-ups. In the Benson's book and in NIST, they tabulate them at specific temperatures. So they give you some points, heat capacity at this temperature, this temperature, this temperature, and they expect that you would interpolate and integrate if you need it, when you need the integrals. Use those as the interpolants. Then there's some expansions. There's a thing called the Showmate expansion and the Wilhoit expansion. The Showmate one is used in some of the NIST tables, but not all of them. I don't know why. For a while they were into it, and then they stopped. Wilhoit one has some nice properties about having good behavior at asymptotically high temperatures. However, unfortunately, the original paper had a bunch of typos, so the formulas were wrong. So this caused massive confusion. So some people used the formulas in the paper. Some people re-derived it and got the correct formulas. The whole thing's inconsistent. You have to watch out. If you ever do the Wilhoits, be careful. But the nice property is that they actually have good behavior at the asymptotes. Most people use the NASA formats, which are basically just polynomial expansions for the heat capacity. This is this is very problematic. So one is that a polynomial has no relation to how actual heat capacities look like. Real heat capacities go to an asymptote at high temperature, or have very, very little change. Once the temperature is high enough, they don't change very much. But polynomials change really fast with temperature. And typically, the NASA polynomials go out to like 6th order. So a 6th order polynomial just takes off to infinity or negative infinity as the temperature gets high, which is completely wrong. So then to try to patch it, they patch together two polynomial fits at different temperatures, and they try to patch them at a central point. However, the formula doesn't force the central point to actually smoothly connect the two polynomials. So you typically have a kink at the central point. So if your system happens to work near the kink, you can have a lot of numerical problems because all your capacities have a strange behavior, non-analytic behavior at one temperature. Also, at some point they decide to change the format. I don't know why. So some people have NASA polynomials like with 12 coefficients, and some have 14 coefficients. And so they're like completely incompatible with each other. But they're both called NASA coefficients. So just anyway, if you're into this, you get into these codes, you have to read the descriptions, exactly what they are, pay a lot of attention. It's very, very easy to screw it up. And if you screw up your fundamental thermo, the rest of your model is going to be total trash. Okay, so you have to make sure you get it right. But it's very well explained. Actually, the Chemkin online documentation is really very clear about all these different things and explains things very well. So it's worthwhile to read it. But just be super careful. If somebody gives you a thermo file, read what it is. Somewhere they'll probably tell you what it is. Make sure the number of coefficients matches up the number you expect, that the things are in the right columns, because the old Fortran style, you had to have all the numbers in the right columns, and some of the codes require that still be there. If the columns got shifted, you'll be wrong. A lot of things can go wrong. Okay. And the heat capacities, another thing to be aware of the heat capacities, at low temperature for condensed phase, it's very easy to measure heat capacity. So for stable molecules at low temperature, the heat capacities are usually really great because somebody actually measured them with a calorimeter. And you can, there's very, very good quality scanning calorimeters that can measure many significant figures. So the condensed phase stuff is usually brilliantly great as long as somebody measured it. However, for gas phase, it's super hard to measure heat capacity. Almost nobody has an instrument that can do it. The accuracy is not that great. So almost all the gas phase heat capacities, which are exactly what you'll care about, are almost all theoretically derived in some way. And we'll talk about ways that they might have done it. But whether they're really correct, who knows? So beware. So this is a likely source of error, is that the theoretical values that are being used. So you read them in the JANF tables, you might mistakenly think that that's because somebody measured it. Is not true. So it was somebody in 1950 had a slide rule, did the best quick calculation they could of what they think the heat capacity should be, typed it in the table, and since then everybody's repeated that number. And if that number had a mistake in it, well, too bad, you're all wrong. Okay? So just beware. And then there's a lot of people who've tried to recompute these things, and they'll get different numbers depending on exactly how they do the calculation. They aren't that different, so they'll be sounding kind of close. but they're different. And particularly if you're extrapolating to high temperature, like in the exhaust region, it could be very significant because you're integrating these integrals over a very broad T range. Like you go maybe from 298 up to 2000 Kelvin. And that's a really big integral, and this term will be the dominant part. This part will be small, and this will be big. Or same thing here. And so if you have an error over there, it could really be very important. All right, this is what you see in tables. So this is kind of typical. You have like a enthalpy of formation, an entropy of formation, and then values of heat capacity at several different temperatures. And different people use different temperatures where they record it at. And they report a whole lot of decimal places here, but they don't know them. So really, this is only probably good to the first two significant digits. And all those decimal places baloney. But somebody just typed it out. So I don't know why. But that's what you'll see in tables. All right, and you can look them up. A lot of them on the NIST, National Institute of Standards and Technology, has a lot of the Thermo. Very convenient source for common molecules is called the Webbook, webbook.nist.gov. And you can just type them in, and they'll give you the values for you. They read the footnotes. So those numbers that NIST gives always have a description of where the number came from and their estimated error bar on the numbers. And pay attention to the error bars, and you'll see the error bars are pretty big sometimes. Sometimes not. Sometimes they really know it. More recently, a lot of people started using quantum mechanic calculations to calculate a bunch of the numbers. And particularly for the heat capacities, it's actually probably better than the old numbers. And so there's a bunch of those. And one of them is called this Third Millennium Thermodynamic Database. See, Third Millennium Thermodynamic Database. This says 2005, but actually there's more recent versions. And there's a person named Elke Ghost in Stuttgart who maintains this database. And they keep on adding more and more compounds with improved values for thermochemistry as best they can get them. This database does not give error bars. And it's a lot of the numbers in there are from quantum chemical calculations, which may be correct, but may not be, and often not checked. So they might be correct, but if they were wrong, they might not know because there's no number to compare with. The reason why they did the quantum calculation was nobody had ever done an experiment on that species. So they just had to get the number. Some of them are from experiment, and some of them are super great. So some of them are really perfect numbers, and some of them are total baloney. And it's all mixed up together in one big database. So just be aware. And in general, databases online are like that. They're like whoever types something, they put it on the table. And a lot of times they omitted to mention the error bar. And so some of them will be great numbers with really teeny error bars and known to 7 decimal places. And some of them will be like just somebody's wild guess. I need the number today. I just typed in a number, and that's it. And if you just use it, well, you get the quality that you paid for. You download it from the internet without paying anything, and you got nothing. So you have no reason to be annoyed at them because you didn't do anything either. This is the format for the this is the NASA polynomials. This thing here, T low, T high, and T mid. T mid is the temperature where they switch the fits. They have one NASA polynomial fit at low temperature, another one high temperature. The user can choose what value to use for T mid, where to connect the two of them together. And if you download a file like this, you are counting on that user to have done a really good job with their fitting and to make a really nice, smooth connection between the two polynomial fits, which might be true, but you're counting on them. If you don't check it, I'd highly advise write a little program that just plots these out and just see if they look reasonable. If they go crazy off to infinity, if they have big kinks, the stuff like that, then you may want to go and refit the data yourself and look it up yourself. Again, if the numbers are bad in the Thermo, your whole calculation is going to be bad. These are the adiabatic flame temperatures computed for different equivalence ratios. I think this is for methane. Actually, for a bunch of fuels. Sorry. Yes, methane, propane, benzene, ethylene. And this is typically what you see is that near stoichiometric, you get very high adiabatic flame temperatures. The adiabatic flame temperature is what if you solve for the equil calculation, and you solved for a mixture that was adiabatic, that was whatever ratio here of fuel to air, for the near stoichiometric, all these numbers are really high, over 2,000 Kelvin. And so that's true. The flames would be super high. And then when you go on lean side or rich side, you get much lower temperatures because you're using a lot of your heat from the reaction to heat up the excess reagent. Right? You have either left extra air or extra fuel, and that's not doing any reactions for you, and you're just using the heat to heat them up. All right. And by the way, you can see why you have things like the poor combustion in the lean side is that the adiabatic flame temperature is only like 1,000 Kelvin. You basically, even if you burned all the fuel to completion, you don't have enough heat to actually make the reactions go very fast, even with no heat losses. Let's see. If you run the Equil program for the adiabatic flame stoichiometric at different pressures, this is what you get. As you'd expect, you get mostly steam and CO2, but you also get quite a significant amount of CO at equilibrium. So when you run an engine and you make CO, part of it's because your engine's not tuned perfectly and not working great. But part of it is that even if you work perfectly at equilibrium, you're still going to make a lot of CO. And so this is a problem. And you have leftover oxygen all the time, too, which is pretty, I was surprised to learn this, but just the thermodynamically, you have some oxygen left over. And you make quite a huge amount of OH radicals. So this would be like up to about 1% by mole of the whole mixture will be OH radicals. They are really reactive. That's a lot of OH radicals. And that's partially the reason why the chemistry runs super fast in the exhaust region. All right. Let's see. Here we go. So entropy has there's a thing called the third law of thermodynamics that basically defines what's the standard entropy. So we define the zero of enthalpy to be 298 Kelvin elements in the standard state. For entropy, the community decided that the entropy of any perfect crystal at 0 Kelvin is defined to be 0. And so then you know the beginning of the integral that you need. Let's see if I have the formula here. Yeah, so the integral is from 0 Kelvin up to here, but we've defined this term to be 0. If the material makes a crystal at 0 Kelvin, then this is 0. And so you only have to know the heat capacity in order to compute the entropy. And so that's called the third law. The third law way of computing entropies is to measure the heat capacities, compute this integral, and that tells you what the entropy is at any temperature. And then in condensed phase, it's easy to measure the entropy. So the low temperature part, you can just measure it. And it's only when you get to the gas phase you start having trouble. And then you have to do quantum calculations or some other calculation to calculate the CPs. The second law method is different. Second law method says measure an equilibrium constant. And the equilibrium constant, if you can measure the K, then you can infer what the delta G of the reaction must be, because they're related by the simple formula. And then if you know delta G, and if you already know delta H, then you can infer what delta S must be. And delta S of a reaction follows a similar equation to Hess's law for the enthalpy, so it's just the products minus the reactants. And so if you know most of the species in a reaction and you don't know one of them, you can use this method to figure out the missing one. And so this is a good method for unstable species. So for radicals, it's not too hard to set up a situation where you have one radical reacting with something in equilibrium with another radical making something else. And if you can attain that equilibrium and make it stable enough, you can measure the ratio or the concentration of that radical, of all the radicals of the system, and infer the K equilibrium by just actually measuring the species concentrations. And then you can work out this. And in fact, you can even get the delta H by measuring this K at several temperatures. There's another law whose name I've forgotten. That's the formula for how you can calculate delta H from K as several T's. And then you can get that just by measuring the K at a couple different temperatures. The key, though, is you have to be able to get absolute concentrations of the species, and you have to really be at an equilibrium to do it. But then you can get the S's, and that's just good for these gas phase unstable species. For the stable species, mostly you get them from the calorimetry integrating with third law methods. I think now I'll stop, and we'll start next time with statistical mechanics.